Okay, so last video we talked a little bit about matrices in terms of what they are, how we can get from a system of equations to a matrix, and then how we can use back solving and row reduced echelon forms to find the given solution to that system of equations. So this video I want to take it a little bit further. I want to go through what consistency means in terms of how many solutions you should expect to have from a given set of equations, and just go through some examples of that. So we'll go ahead and get started. Call it chapter 2, I guess, still. I'm going to call it consistency. So it's not really a textbook chapter, but it's just a topic. And hopefully I spelled that right. But last video we covered this system of equations, 2x plus y is equal to 5, and x minus y is equal to 1. We were able to put this into the following augmented matrix, augmented with 5, 1, and we found that our solution to this equation was x equals 2 and y equals 1. Okay, great. But there was one assumption we made. We kind of just stopped once we got to this point, right? We didn't really look for any more solutions. So how did we know that this was the only solution? Why am I confident in saying that, say, 92 and negative 16 does not also solve the systems of equations? And so you can pause and think about it if you'd like, but one way of thinking about the systems of equations that we're given here actually is as lines in the plane. So you have a function in two variables, x and y, so you might as well graph them in the coordinate plane. So you have 2x plus y is equal to 5. If you move stuff around to get into a better graphing form, it looks something like this. So this is 2x plus y is equal to 5. And then x minus y looks something like this. This is x minus y is equal to 1. And we know that they intersect at this point here, 2, 1. Okay, and so just looking at this picture, we're pretty convinced that we're only going to have one solution. And why is that? Because these two lines are never going to intersect ever again, right? There's no reason that this line 2x plus y is equal to 5 is going to do something that looks like this, right? That's not how lines work. So just by looking at this picture, then, we're able to be fairly confident that this will be our only solution. So let's just forget this example for a second. Let's look at the other cases we can have if we're given a 2x2 system of equations here. So here in this particular case, I had one solution. Is there a possible case where we have no solutions? Yeah, so if I draw my coordinate plane again, let's say I make my first line look like this. And then if I make my second line perfectly parallel to it, so they're never going to intersect ever, then I have no solution. Meaning my lines will never intersect. And we call this, in Math 240, inconsistent. We have no solutions here. And there's one case that actually gets overlooked pretty often. And is there a way that we can actually have infinite solutions? So is there a way that I can draw two lines such that at every point they're equivalent? Well, yeah, I can. So if I draw my coordinate plane again, I can draw my first line look something like this. And then I can draw my second line right on top of it, like that. And in this case, at every single point along that first line, I have a solution to my system because it's overlapping. So in this case, I have infinitely many solutions. So in the case where we have at least one solution here and here, we call this consistent. So if I have a solution that's consistent, if I have infinitely many solutions, it's consistent. I just need, at least one. Great. Okay, and so this was a pretty basic example. Still, we're sticking with 2 by 2, but we were actually able to generalize this to higher dimensions as well. It's just easier to visualize in 2 dimensions. So the book does a pretty good job of explaining it in terms of 3 dimensions. I'm not going to do that generalization here. And they use a bit tricky notation that I don't really necessarily like. But anyway, in order to generalize this to more or higher dimensions, we need to consider something called rank. And so what we can do is we'll first do a few examples of 3 by 3 matrices, and then hopefully by doing these examples we can see exactly where rank should come into this formulation of this into higher dimensions. So if I start with the systems of equations here, x plus y plus 2z is 1, 2y plus 3z is equal to 2, and x plus 2y plus 2z is equal to 3. You should feel pretty comfortable setting this up as a matrix, so I'm going to skip that step. And so I have 1, 1, 2 augmented with 1. I have 0, 2, 3 augmented with 2, and then 1, 2, 2 augmented with 3. So from the previous video on row reduction, we know how we can solve this. We go through and we do those row operations. I'm going to skip those as well. But if you get all the way to the end of it, you have 1, 1, 2, 0, 1, 0, 0, 0, 3, augmented with 1, 2, and negative 2. Okay. So this is going to be my stopping point. You'll see it's pretty much in reduced echelon form. I don't want to really divide that by 3 right now, but I'll have to eventually. So now I can read off my systems of equations. So I have the top row reads x plus y plus 2z is 1. I have y is equal to 2. And I have 3z is equal to minus 2. So right off the bat, I can say that z is equal to negative 2/3, y is equal to 2, and then if I plug those in, I should get that x is equal to 1/3. Great. So then my solution is 1/3, 2, and negative 2/3. This is my solution here. Okay, so note here that we had the case where we just have one solution, right? Now let's look at a different matrix. Let's do 1, 2, 3, 0, 1, 2, 0, 3, 6. Let's augment that with 1, 2, and 6. So I'm actually going to do one step of row reduction here because it's very important to see what's going on. So what I'm going to do, the first column's fine, right? I have a leading one, and then I have zeros underneath it, so I can keep the first row the same. I have a 0 right underneath it, so I'm going to keep the second row the same. And then I'm going to try to get rid of the 3 right underneath this 1 here. I want to get rid of this to get it into row echelon form, right? Because I need a 0 there. So what I'm going to do is I'm going to take row 3 and I'm going to subtract 3 times row 2, 3 times row 2 off of row 3. And so 0 minus 3 times 0 is 0. 3 minus 3 times 1 is 0. 6 minus 3 times 2 is 0. And 6 again minus 3 times 2 is 0. Okay, so I'm done now, but this looks a little weird, right? Let's read off the system of equations here. So I have x plus 2y plus 3z is equal to 1. I have y plus 3z is equal to 2. And then I have this really weird equation at the bottom. I have 0 is equal to 0. Now, when is that true? Well, the answer is always. 0 is always equal to 0. So in this case, we're not allowed to use this equation. It tells us nothing about our system of equations whatsoever. And you might say, well, that's kind of a problem, right? Because I can solve for two of the variables, but I'll need a third equation to solve for the other. And so this is where we start having to define free variables. So the rule of thumb here is you have to define a free variable for the column that has no leading one. That's just the rule. If you do it for, so in this case, right, the column that doesn't have a leading one is this third column here that corresponds to the variable z. So I need to make z my free variable. If you make x and y your free variable, you get funky answers, and you don't want that. So what I need to do then is I need to define a free variable. So I'm going to say that z is equal to t. And what does that mean? I'm going to let t be any number I want. So I'm going to say t is an element of the real numbers. So t can be 0, t can be pi, it can be 1, it can be -7, it can be any number. And what that allows us to do then is it allows us to kind of pinpoint an exact answer if we input a t. So you'll notice, like we said earlier, 3 equations, 2 unknowns, you're going to have infinitely many solutions. However, if you input a specific value of z, you'll be able to pinpoint an exact solution. So all this lets us do is figure out what the form of the infinitely many solutions are going to be. Okay, so I can plug in t for z, and I'll get y. I'll start with the top one, I guess. X plus 2y plus 3t is equal to 1, and y plus 3t is equal to 2. So this tells me then that y is equal to 2 minus 3t, and then z is equal to, oh, sorry, not z. X is the one we have to solve for still. X is equal to negative t minus 3, and then z is just equal to t. So our solution then looks something like this. And I should say solutions. Negative t minus 3, 2 minus 3t, and t. And I have to let t be any number I want. So, like I said earlier, if I pick t to be 0, so if t is equal to 0, then my solution here will be negative 3, 2, and 0. So this is just a way of figuring out exactly what the infinity solutions that we have look like. But this is just a way for me to demonstrate that there are cases here, when you look at this matrix here, that give you infinitely many solutions. Okay, so that takes care of 2 of our cases, right? So we have one solution and infinitely many solutions. And now we have to look at the case where you have no solution. And this is a bit tricky in the 3x3 case. So let's look at this matrix here. We have 1, 2, 3, 2, 6, 2, 1, 3, 1. Then I have 0, 1, and 2. Okay. So if I do row reduction again, I'm not going to do it out. It might actually be good practice for you to do. But I end up with 1, 2, 3, 0, 1, negative 2. Oh, let me redo that. That's kind of off. 0, 1, negative 2, 0, 0, 0. So I have that same row of zeros at the bottom. But on the right-hand side, I'm augmenting it with 0, 2, and negative 3. Okay. So let's read out the system of equations as we always do. So we have x plus 2y plus 3z gives me 0. Nothing wrong with that. Next line says y minus 2z is equal to 2. That's a 2. Let's redo that. And And then finally, our last line tells me 0 is equal to -3. Okay, so obviously we have a problem, right? Is 0 ever equal to -3? No, not in this universe. So that's bad. We don't want that. So we say then that since 0 is never equal to -3, I'm never going to be able to have a solution. This corresponds to, in the analogy, the case where you have two parallel lines. If you want to read up on what it looks like in the 3x3 case, you can check the textbook. But we will never be able to find a solution that solves this particular system of equations. So we call this inconsistent. Okay, so you might have noticed a little bit of, like, not a pattern per se, but you might have noticed exactly what about the matrix at the very end, or the row-reduced matrix, makes it consistent versus inconsistent. So you might notice, for instance, here, that we had an entire row of zeros at the end, right? And that gave us this weird 0 = 0 equation, which we couldn't use. And so you can kind of think of it as though, like, if you have a row of zeros, you're gonna, like, a row of zeros across the board, including the one on the augmented side, then you'll have one of those 0 = 0 equations, and you have to lose a variable. You're not going to be able to write a unique solution to this problem if you have a row of zeros across the board. Additionally, if you have a row of zeros on this side down here, but you don't have a 0 on this side, then you have the weird case where you have 0 = not 0, which is actually worse. So that's kind of the pattern here that people started to notice, and so someone came up with a way to better define this. It's called rank. So we're going to talk quickly about that, because I know this video is getting long, but rank of a matrix. And rank is simply defined, well, it's defined in a couple ways, but it is the number of non-zero rows in the reduced row echelon form of the matrix. That's cool. Okay. And what rank helps us do is it helps us decide how many solutions we're going to have to a problem. So moving forward in this course, we might not necessarily be interested in the exact solution, like, for instance, 2, 1, like we had in the 2x2 example. But we'll be more interested in how many solutions we should expect to get. So rank kind of allows us to skip a whole lot of the row reduction and actually just go straight through and figure out if we have consistency or inconsistency. I should also note that it's also defined, and some people like this notation better, the number of pivots, which are also called the leading ones, in the reduced row or the row echelon form of the matrix. So we'll talk about how you find this exactly at a later date, but pretty much, or no, I guess I'll just say it now. Pretty much you row reduce your entire matrix, and then you figure out how many non-zero rows you have. It's pretty simple. But I do want to talk about just the formulation a little bit. So if we have any arbitrary matrix A, we say A is m by n, so that means m rows and n columns. We can say that if rank of A is equal to the number of columns, which means that I have a leading one when I row reduce this in every single column, then I should see a unique solution. So Just as an example, this is obviously not a way to prove it, but here we saw that we had a leading one, or we could get a leading one in each of our columns here, and that gave us a unique solution. So that's just an example. And then we have a couple things. So first of all, the rank of A can't be bigger than n, right? You can't possibly have more pivots or leading ones than you have columns, because that would be ridiculous. That would be the equivalent of you having a pivot over here, which you just can't have, obviously. So instead, we can say that if rank of A is less than n, which we saw in two cases, right? We saw here's a 0 row here. I forgot. Right here is a 0 row, and right here is a 0 row. You can have two possible things. And those things depend entirely upon what lies here and what lies here. So if rank of A is less than n, we can define this equation, just to make notation easier. Ax is equal to b, where b is the stuff that is augmented. So A augmented with b, like this. It's just a column vector. B can also have a notation of rank, right? It is technically a matrix, and its rank would be the number of non-zero entries. So if rank of A is less than n, and the rank of B is equal to n, then you have no solution. So that means that if I have rank of A less than n, which means I have a 0 row in my matrix A, this one here, but I don't have a 0 in that same spot here, then I will have no solution. However, if my rank of B is less than n, then I can have a 0 in that spot down there, and I have no problem. And in fact, I'll have infinitely many solutions. So again, the reason we talk about rank is more of just from a theoretical standpoint, being able to skip the calculations and decide for yourself how many solutions you should expect to have in a given system of linear equations.